Okay, here is the follow-up lecture for Chem 3043, March 25th. And what I'm going to do is the requests have been to go over the multiple choice problem from problem set 19b. And this essentially is going to cover this question here, the difference between Lindlar's, lithium and ammonia, and H2 and palladium. Then I'm going to talk about problem set 19, problem 5b, and then problem set 19, problem 10e. So, starting out with the multiple choice problem, we have an alkyne, and essentially we make this compound right here. Even though it has deuteriums on it, deuteriums are just hydrogens, this is simply an alkane. So what we have done is we have reduced the alkyne to the alkane, or another way of thinking about it, we have added 2 Ds and 2 H's across the alkyne. Now, our choices, how to do this, well, the way we can react alkynes is we can bring them down to alkenes and alkanes. And our main choices of reacting with alkynes at this stage is we can use palladium on carbon, and this is essentially the most powerful reducing agent that we have. It takes alkynes all the way down to alkanes, which in a way is kind of what we want to do. And it does this by adding deuteriums, syn, to each other. But the issue is, it is too strong. It doesn't stop at the alkene. It keeps going and adds 2 more deuteriums to that. Giving this as a product. So you end up adding 4 deuteriums total to the alkyne, and you end up with this. If you want to stop at the alkene, you need to use what's called poison palladium, or a weakened form of palladium. In this case, the weakened form of palladium that we have is what's called Lindlar's catalyst. So instead of palladium on carbon, we use D2 and Lindlar's. And that puts the deuteriums here. And this right here does not react with Lindlar's. Lindlar's is weak. It typically just reacts with the alkyne and not with alkenes. Now that gives us a cis-alkene. If we want the trans-alkene, we would need to use lithium and ammonia. Now that adds hydrogens trans to each other. If we want to add deuteriums trans to each other, you need to understand where these hydrogens come from. And they come from the ammonia. So if you wanted to add deuteriums, instead of using lithium in NH3, use lithium in ND3. And then you don't have any further reactions because this isn't strong enough to react with. It's not strong enough to react with alkenes, just alkynes. So these are the 4 methods. And it's important to know which ones add syn and which ones add anti. These conditions add syn to each other. That means the hydrogen or deuterium you're adding end up on the same face. With the ammonia, adds anti. So the hydrogens or the deuteriums you're adding end up on opposite faces of each other. So going back to this multiple choice, here if we look, those deuteriums are on opposite faces of each other. They're not syn, but the only way we have to make an alkane is this, which adds hydrogens and deuteriums syn to each other. But keep in mind that alkanes can rotate, and the molecule that I draw might not necessarily be in the right conformation. Remember, this molecule right here, you can redraw it so the deuteriums are syn to each other. And I did that by just rotating. Or you can redraw it like this. So this is the syn conformation, either one of these. And when you do so, you can work your way backwards. So if you do so, the 2 deuteriums adding syn to each other, we would use D2, palladium on carbon. And our starting material would need to be an alkene, because if it was an alkyne, you'd end up with 4 deuteriums, not 2. And the way you draw your alkene is you start by drawing your lines exactly in the conformation shown. See how to make that shape right there? Make that same shape. If the molecule was like this, here they're on the same face of each other, both wedges, then the lines that you would draw would be like so. And then once you have your backbone in, you add in your alkene, where the 2 deuteriums are going to go. So if you start off with the transalkene, you get this product. If you start out with cis alkene, you get this product. This is the one that we want. Then we have a cis alkene. Cis alkene, well, we get that from H2 and Lindlar's. And when we look at our options, we know it's not A. B has Lindlar's and palladium on carbons. That's an option. C has lithium and ammonia. That's not an option. All the above is not an option. So we're down to B or E. Well, if we take a look at this, remember, hydrogen and deuterium are interchangeable. So what you can do is instead of using hydrogen and Lindlar's first, you can go deuterium and Lindlar's first. That adds 2 deuteriums syn to each other. And then if you use hydrogen and palladium on carbon next, that adds 2 hydrogens syn to each other, which they are here. So B is the correct answer. So that covers the multiple choice problem for 19b and the difference between these. Now, problem set 19.5b. Okay, this is a mechanism problem. And it's not a very well-written mechanism problem. Essentially, we have is this molecule here, treating it with water, it's a pretty lousy ring. Let me make that a better 6-membered ring. Okay. So, how this works. Here's a mechanism problem. It's not a predict the product problem. Here's a mechanism problem. We have our alpha carbon. It's secondary, but the beta carbon here is quaternary, so you're not really looking at an SN2 reaction, plus water being the nucleophile. We're looking at an SN1 reaction. You have the leaving group leave. And you get this carbocation. Now, this carbocation, let's see if we can draw that carbocation out just a little bit better. It's secondary, right next to a tertiary one, and either of these groups can migrate, and this can swing upwards to that. There is no stereochemistry to this. This group, if we kind of look on a side view, that has an empty p orbital. And essentially what we're doing is we're shifting this bond over to one of those two sides. If it shifts over on to the bottom, if it shifts to the bottom lobe, that pushes the hydrogen upwards. And would likely give you this carbocation. If it shifts over to the top lobe, then that pushes the resulting hydrogen downwards, giving you this carbocation, and then the water can add from either side of that. So this was a bad problem. I don't, mainly because of the stereochemistry of this. One of these two stereochemistries is preferred. Which one? I don't know. This is one of these things where you would probably build a model kit to figure out which one is actually preferred. But the purpose of this problem was to draw a mechanism from here, the starting material, to these two products, and this is the mechanism to worry about. You just slide this over, and that essentially connects this carbon here to this carbon. If you want, you can number this. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the new bond ends up between carbons 5 and 1. Two, 3, 4, 6, 7, 8, 9. The carbocation ends up on carbon 2 because we're moving the electrons away from carbon 2. So the carbocation ends up right there. It can be transferred to the top side or the bottom side, so either of these two. And then water can add. To that. So. And we can add from the top or the bottom face. And then you take the proton off. So that's the other issue of this problem, is I'm not listing out all of the products of this, because water can add to the top face of this one and bottom face of this one, top face of this one, bottom face of that one. So there are actually, technically, a couple more stereoisomers possible. Try this one. That's if it adds to the opposite face. And then this one right here, if it adds from the opposite face of the hydrogen. So technically, you should be able to get all of these products. Each one of these, since the starting material started out as racemic, each one of these would be racemic. And so there ends up with 2, 4, 6, 8 possible products, because you have 4 chiral diastereomers that are possible. And each one of these diastereomers is chiral, so you have each one of their enantiomers as well. So there's actually quite a few more products, I just didn't list them all. Okay, problem set 1910E. E. 10 is a synthesis problem. Synthesize from 7 carbons or fewer. And the carbon containing molecules cannot be ionic. Okay, so 10E. We start with this. And I suggest molecules like this, it's a good idea to number. Now, this molecule here is an ether. That's that connection right there. And the way we make ethers is by an SN2 reaction. And there are two possible bonds to make this ether from. You can split it right here, in which case yeah, this is a possibility. Or you can split it on the other side. In which case, this is your possibility. You just got to figure out which carbon has a leaving group on it. It's 9 carbons. The chain needs to be 10 carbons long. We're attaching it to carbon 5. So I'll put carbon 5 here. I'm going to give it bromine. And since the product is racemic, this also has to be racemic. So does this. Okay. Now, these two roots are not equal. You can do this root right here. You cannot do this root. Mainly because if we take a look, the alpha carbon here is an sp2 alpha carbon. And you can't do an SN2 reaction on a benzene ring. So this doesn't work. So you have to use this method. This molecule here, we have to make because it has 6 carbons, so that's 7 carbons or fewer, but it's ionic. And so the way we make an O- is that we make it from an alcohol. Or in this case, technically, we make it from the phenol. And we essentially deprotonate this. You can use sodium hydride, but that's overkill. In real life, chances are you would just use sodium hydroxide or potassium carbonate, either one. If you use sodium hydride, we would accept that as well. And now this has 6 carbons. It's non-ionic. You don't have to make it. Check. This carbon, this molecule on the right-hand side, though, has 10 carbons, so we do need to make that. And we have to be able to make it from this bromide from any other material. Bromides can come from alcohols or alkenes. I really suggest you get in the habit of working backwards to the alkene, because from the alkene, you can go backwards to the alkyne. So we can work our way backwards. And the alkene can appear in one of 2 different places. We go from the red we get that alkene. If we use the blue, we get that alkene. And let me make sure I count this right. 3, 4, 5, 6, 7, 8, 9, 10. In the red, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, one of these is better than the other, because the way we go from an alkene to a bromide is we add HBr. This is an addition reaction. And you protonate to form the most stable carbocation, and the Br goes on the more substituted side. Well, the problem is carbon 4 is equally substituted carbon 5. And so if we were to do HBr to this, we would get the bromine on carbon 4. Oops, one too many. Or you get it on carbon 5. If we use the blue molecule, we would get on carbon 5 where we want it to, or we would end up getting it on carbon 6. So, the red alkene goes to these two possibilities. The blue alkene goes to these two possibilities. And remember, the possibility that we want is this one right here. These molecules are constitutional isomers. Different connectivities. These molecules, on the other hand, are the same. Because if you number 1, 2, 3, 4, 5, the bromine's on carbon 5. If you number from the right over here, or, oops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Too many carbons. That's a problem. Definitely pays to help with the carbon counting. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Here's the bromine. Now this is correct. Because if we count this way, it ends up on carbon 6. But if you notice, if you count the opposite way, 1, 2, 3, 4, 5, the bromine ends up on carbon 5. And so these two are the same. That's what makes this alkene a better alkene than the red one. So that's the alkene we want, is between carbons 5 and 6. Now, I drew that double bond as trans. I could have just as easily have drawn that double bond as 6. It actually doesn't matter which one you add the HBr to. You can add the HBr to this alkene, you get this. You can add the HBr to the cis alkene. It doesn't matter which one you do it. So just pick one. If you choose the trans alkene, you would make that with lithium and ammonia. If you were to choose the cis alkene, you'd make that with H2 and Lindlars. But regardless which one you choose, the alkyne ends up being the same, with the alkyne being between carbons 5 and 6 because the alkene is between 5 and 6. And then we have to make that alkyne. And there are two ways of making this alkyne. We make alkynes by an SN2 reaction. And so you cut the carbon-carbon bond next to the alkyne. The sp carbon, you can draw it as a lone pair to make it the nucleophile, or we can draw it as a sodium salt, either one. And carbon 7, that's the electrophile, gets a leaving group. To make, now this has 1, 2, 3, 4 carbons, that's 7 carbons less, it's non-ionic. Check. We don't have to make it. This has 6 carbons, but it's ionic, so you do need to make that. And the way you do that is you make that by just an acid-base reaction. And the base that we used is sodium amide, NaNH2. Sodium hydride does not work. Sodium hydride has a tendency not to be able to deprotonate carbons. It just deprotonates oxygens and nitrogens and sulfurs. It doesn't deprotonate carbons. And that gives that there. That has 6 carbons. It's non-ionic. You don't have to make it. That's one way of making this alkyne. Another way of making the alkyne is realizing that the two R groups attached to that alkyne are the same group. This group, 4 carbons, is the same group as that. And when they are the same group like that, you can do a specialized trick where you can add them both at the same time. You do that to a doubly deprotonated alkyne. And then you have to use excess sodium amide, because if you use one equivalent, that means you just deprotonate the alkyne once. So this is one of the few times you do have to say excess, because one equivalent, if you just write NaNH2, we are going to assume that just deprotonates once. But if you have excess, it deprotonates twice, and then this is added to both sides of it. But this trick can only be used when the two groups attached to the alkyne are the same group. Okay. So, that's all I've got, and tune in next time. We're going to be talking about OHs, alcohols, and how to turn them into good leaving groups. Additional methods that aren't quite as harsh as HBr.